Hello everyone, I'm Jiayu Zhang from Zhongguancun Laboratory, and I'm very happy to talk about my work, formulation and constructions of remote state preparation with verifiability with applications. So this work is about an important quantum cryptographic primitive called RSPV. We will talk about its backgrounds and talk about our contributions on its framework, constructions, and applications. So let's start with the backgrounds. So what is an RSPV? This is a basic primitive in quantum cryptography. Let's consider the following setting: the client and the quantum server. And the client would like to send some state to the server, where this state is randomly sampled from the state family. The simple solution is to use a quantum channel. So what is the output of this simple protocol? The output is as follows. The client knows the state description, and the server simply holds the states. We note that in the quantum world, holding state description is much more powerful than holding the states. So starting with this output, the client and the server could perform some further cryptographic tasks. But we could see the simple solution use quantum channel. So what if the client is completely classical? Could she achieve the same thing over a classical channel? So that the output is still the same or indistinguishable in a sense to the quantum channel output. So we would like to design a cryptographic protocol to achieve these tasks. We could use cryptographic assumptions. And the soundness should hold, which means even if the server cheats, either it is caught cheating or what it gets is normal than the only setting outputs. So this is an important primitive. On the one hand, you could serve as a protocol compiler. You could imagine with this primitive, we could design cryptographic protocol in the following way. We first design a quantum protocols which use quantum communication, and then compile it using RSPV to a protocol which only uses classical communication, which is more desirable. And this technique has become an important tool for many other problems, including classical verification of quantum computations, CVQC, which is an important quantum cryptographic primitives. And there are also some other works which use RSPV. I will describe my one application in my second talk. And there are many results on RSPV primitive. But existing works on RSPV also have limitations. On the one hand, there are some variants and subtleties in the definitions. Even defining the primitive is not very clear. And existing works only focus on simple state families, like single qubit states plus theta states. But we want to get RSPV for more general state families. And we also want to see more application of RSPV. So corresponding to these problems, we study its formulations, construction, and applications. So let's go to our contributions. We first give a framework for constructing RSPV. And the motivation is to construct more advanced RSPV, for example, for more advanced state families from smaller pieces. We choose more well-behaved variants of notions for RSPV, and we prove some abstract properties, including sequential composition and soundness amplification. And these abstract properties will be used later in concrete constructions. In more detail, we prove the sequential composition, which means if we are given RSPV for state family F1 and F2, we could perform these two RSPV sequentially, and we could directly get an RSPV for the tensor product of F1 and F2. This is a desirable property. We also prove the soundness amplification, which means that we could first construct a pre-RSPV, which is a relaxed variant of RSPV. This is easier to construct, and then we could amplify it to an RSPV. And we also introduced a new primitive called remote operator application or verifiability, or ROAV. This is a new cryptographic analog self-testing, which is also a popular topic. We omit this in this talk, and we know that the concrete constructions for a trivial ROAV is still an open problem. So let's go to our concrete constructions. We can draw RSPV for a new state family, 0 plus 0 plus 1x1, where x0 and x1 are long strings. This is sometimes called the closed states. And we also recover existing results in a more modular way, which is a plus theta states, where theta is from, where theta could take 8 values. So this is sometimes called the 8 basis Q factory. So the overall approach is to give a sequence of reductions between different RSPV primitives. We start from RSPV for BIP84 states, whose protocols is given in this paper from relatively weak assumptions. And starting from this RSPV, we construct new RSPV protocols step by step, where each RSPV builds on some other RSPVs that are simpler to construct. And each step is either a direct application of our framework or something information theoretic, which are easier to analyze. And this is our reduction sequence. We start from BIP84 states, and we construct new protocols step by step. And we construct the RSPV protocols for 0 plus 0 plus 1x1, and we further construct the RSPV protocol for plus theta states. Here, the blue arrow is by our framework, or something very simple. And the red arrow is by analyzing an information theoretic core. Let's give an example. Let's focus on the first arrow and see what happened here. As an example, the first step, our reduction, is to start from the BIP84 states and construct an RSPV for the x0 plus x1, where x0 and x1 differ in only 1 bit. So we note that for the state in this form, it is equivalent to write it as the tensor product of lot of 0 state, 1 state, and a single plus states. And this means that we could to construct the RSPV for this state family, we could first perform sequential repetition for RSPV for BIP84 states, whose soundness is directly implied by our framework. And then the client will pick the states needed and discuss the others. So we also apply our results to the classical verification quantum computation problem. We construct CVQC from weaker alternative assumptions. So what is CVQC? This is another important primitive in quantum cryptography. In this problem, the client would like to ask the server to perform some quantum computation for it, but the server's output is not trusted. So the client would like to use a cryptographic protocol to verify the output of these quantum circuits. Roughly speaking, existing CVQC relies on learning with error assumptions, which is a cryptographic assumption. This is good, but we still want something better. By our work existing results, we construct CVQC from alternative assumptions, which is called cryptographic group actions, which is killed even if LW is broken. We note that after our work is made public, we are aware of some alternative approaches or concurrent works for these results. Group action-based CVQC. There are two existing current works, which is one is via previous state preparation, and the other is via compiling network games. And we also get aware of an additional approach from an anonymous reviewer by a paper by Mah18. So in summary, we developed a framework for constructing LP protocols. We construct SPV for new state families and recover existing results in a more modular way. And we, as an application, we construct CVQC from cryptographic group actions. And there's an interesting open problem, so which is how could we construct SPV for general state families? Thank you very much.